In this video, we will look at how to use factoring to solve quadratic equations. Before we are able to do this, we need to identify a fundamental concept upon which all of the solving will rely. In Part A, if we are told two numbers multiply to make 12, what are those numbers and why? If we start to think about numbers that multiply to make 12, we have 1 times 12, we have 2 times 6, we have 3 times 4. But the fact is there's other numbers that also multiply to make 12, -1 and -12. But there's other ones that you wouldn't immediately think of. 7 times 12 over 7 is also equal to 12. The fact is, for almost any real number you give me, I can find another number we could multiply your number by to obtain 12. So the fact is, if we're told two numbers multiply to make 12 and asked what are the numbers, we have no way of knowing. On the other hand, in Part B, if we are told two numbers multiply to make 0 and what are the numbers, this is a very different situation. If two numbers multiply to make 0, the only way that can happen is if one of the numbers itself is 0. So if we're told two numbers multiply to make 0 and asked what are the numbers, at least one of the numbers must be 0. The reason for this is the only way to multiply two numbers and make 0 is if one of the numbers is 0. This brings us to the zero factor theorem. It is basically that concept. If two things multiply to make 0, one of them has to be 0. But it's applied a little bit more broadly than just numbers. So the general way we state this is if a times b equals 0, then either a equals 0 or b equals 0. And this statement applies not only to numbers, but will also apply to expressions. A and b could be expressions, or they could be numbers. In Part D, the question is, what is the standard form of a quadratic equation? The standard form of a quadratic equation is taking the standard trinomial that we've worked with before, ax squared plus bx plus c, and setting it equal to 0. One key note is it would not be a quadratic equation if the a value was 0, because if a was 0, there'd be no x squared, and if there's no x squared term, it can't be a quadratic equation. But in Part E, why do we have to set it equal to 0? The reason it must be set equal to 0 is so that we can factor the polynomial on the left side of the equation, and once it's factored, we can then apply the zero factor theorem. So now let's make use of that zero factor theorem to solve two equations in Part F. The first equation in Part F is the equation quantity x minus 3 times the quantity x plus 4 equals 0. It's important to recognize we already have multiplication, so this equation is already set up with two things multiplying to make 0. So if these two things multiply to make 0, one of these things must itself be equal to 0. So we can split apart this quadratic equation into these two separate smaller equations. Either x minus 3 equals 0, or it's the x plus 4 that equals 0. But the only way these two things can multiply to make 0 is if one of them individually is equal to 0. You'll notice we've taken something that was a quadratic equation, and we've now split it into two separate linear equations. We'll solve each one of those on its own. If x plus 3 equals 0, I can add 3 to both sides of the equation to get x equal to 3. Or on the other hand, if x plus 4 equals 0, we can subtract 4 from both sides of the equation to obtain x equals -4. While it's not explicitly asked for, it's always a good idea to check your solutions. To check if 3 is actually a solution for this equation, we'll always want to return to the original equation and substitute 3 in for all of the x's. So the original equation had been x minus 3 times x plus 4 equals 0. Substituting 3 for those x's, we would have 3 minus 3 times 3 plus 4, and we'd be asking, is that equal to 0? Well, in the first set of parentheses, 3 minus 3 is 0. In the second set, 3 plus 4 is 7, and we do know that 0 times 7 is actually equal to 0. So 3 definitely checks out as a solution. To check whether -4 is a solution, we'll do the same thing, except we'll substitute -4 for the x's. So x minus 3 becomes -4 minus 3. X plus 4 becomes -4 plus 4. And we're checking, does that actually equal 0? Negative 4 minus 3 is negative 7, and negative 4 plus 4 is 0. Negative 7 times 0 is 0. So negative 4 also does check out. As always, when we're solving an equation, we will finish with a conclusion. And so in this case, the conclusion would be the solution set is the set 3, negative 4. The second equation in part F that we were asked to solve is t squared minus 7t equals negative 10. There are two substantial differences between this equation and the original. First, this equation is not set equal to 0, and second, it is not already factored. So we need to do both of those things. The first step must be set it equal to 0. So to set this equation equal to 0, we will need to add 10 to both sides of the equation. By adding 10 to both sides of the equation, we'll have t squared minus 7t plus 10 equals 0. At this point, we want to factor it using our general factoring process. First thing, we look for a greatest common factor. Looking through the polynomial on the left side of the equation, the greatest common factor is 1. Again, looking at the left side of the equation, t squared minus 7t plus 10, to factor that, I recognize it is a trinomial. And not only is it a trinomial, it's one of the nicer ones, where a is equal to 1. Since the a value, the leading coefficient, is 1, I can turn my attention to the c and the b, and answer the question, what multiplies to make c and adds to make b? So our c value is 10, so we need to find two things that multiply to make 10 and add to make negative 7. It's good to pause and remember, since the 10 is a positive, both numbers will have to be the same sign, and since the negative 7 is negative, both the numbers will have to be negative. So things that multiply to make 10, negative 1, and negative 10. But that does not add up to make negative 7. Another possibility is negative 2 and negative 5. Negative 2 times negative 5 is positive 10, and negative 2 plus negative 5 is negative 7. Since this is one of the nicer trinomials, we can jump straight from the trinomial to its factored version. So we will have t minus 2 times the quantity t minus 5 equal to 0. By now having factored this into two things that multiply to make 0, we get to split this up again. Either the first factor is 0 or the second factor is 0. So either t minus 2 equals 0 or t minus 5 equals 0. One of those would have to be equal to 0 for this equation to be true. To solve t minus 2 equal to 0, we will add 2 to both sides of the equation and get t equals 2. To solve t minus 5 equals 0, we'll add 5 to both sides of the equation to obtain t equals 5. If we substitute 2 back in for the t's in the original equation, we will get a true statement. Similarly, if we substitute 5 back in for all the t's in the original equation, we will also get a true statement. 2 and 5 are the solutions for this equation, and another way we could write this conclusion, instead of using solution set notation, is to simply state the solutions are 2 and 5. When solving a quadratic equation by factoring, the first step is to make sure it is set equal to 0. The second step is to then factor the polynomial that you have. Once it's factored, you will split apart and set each individual factor equal to 0 and solve each of those new equations. It is always recommended that you check your solutions so that you can verify your work was correct.